Hello, I'm Paulo Montero-Camacho, a postdoc at the Department of Astronomy of Tsinghua University, and I'm going to be talking about the Lyman-alpha forest power spectrum as an emerging window into the epoch of reionization. The outline of my talk is the following. First, I'm going to be talking about the state of the intergalactic medium after reionization, and how the reionization process leaves thermal relics in the Lyman-alpha forest that can be seen even at low redshifts, let's say for example redshift of 2. Besides that, I'm going to be talking about how naturally these relics from the reionization process depend on the astrophysics of reionization. Finally, I will be briefly mention how maybe in the future we will be extracting the epoch of reionization astrophysics from the Lyman-alpha forest power spectrum. So, in principle, the dark energy spectroscopic instrument DESI will measure the three-dimensional Lyman-alpha forest power spectrum in the next few years. Such a complicated and amazing measurement requires several assumptions to simplify the pipeline. One such assumption is that the intergalactic medium follows the temperature evolution of the intergalactic medium follows a power law that has this form where gamma is the adiabatic index and is supposed to be constant with respect to redshift. So imagine something like 1.67 since we believe the intergalactic medium is mainly hydrogen, so a monatomic gas. Now, based on that, you will then produce one power spectrum of the Lyman-alpha forest. In this case here, I'm putting the one-dimensional measurement from EVOS as a placeholder since we haven't measured the three-dimensional yet. Now here in this plot, I will argue that we are already seeing evidence for the power law of the intergalactic medium breaking, since it's not really constant with respect to redshift and does not necessarily look like 1.67 either. So I will argue then that maybe it's the fact that the reionization of neutral hydrogen is actually a very patchy process. It happens first around the ultraviolet sources, so stars and galaxies, and then percolates the whole universe eventually. So as a result, then patchiness will naturally break this power law, since some patches of the sky will have already reionized while other patches of the sky will have not. On the other hand, recently we saw that if we zoom in into what is going on in the small scale structure, we see that the power law is also broken again, this time because of the way the gas in underdense region actually reionizes, which reionizes to quite high entropy and then gets even to higher entropy because of shocks from denser regions that will compress the lower density into a gas to mean density and heat up even more the underdense gas. As a result, then you have something that looks like your cosmic wave getting heated to a high temperature, and then the time scales that it gets to dissipate that energy, it's quite cosmological. It's quite large. So what is going on is maybe better explained here in this plot. So in the bottom row, what we have is an early reionization model where the universe reionizes at redshift 10 and time is moving to the left. So also what we have here is wherever there is more blue, then is basically more gas present. So we see that even if we see a redshift of observation 5 in this log temperature log density plot, we have basically a very compact structure, which basically is consistent with a power law of the power law form that I described earlier of the temperature density relation. Now, however, if we move to the late reionization model, let's say a universe that reionizes at redshift 7, then we see that we have indeed a considerable population of gas that is in the region consistent with that power law, even at redshift of observation 5, so early after reionization. However, we see a different mode, the high entropy mean density mode, if you will, that lags behind and takes cosmological timescales. Even at redshift 2.5, we have not recovered the power law as it should be. So now the question is, how does this look like in the Lyman-alpha forest power spectrum? So here in equation 1, I put basically a traditional form in the first term of the right hand side of the Lyman-alpha forest power spectrum. and then my additional perturbation, which just corresponds to mainly this key matter and neutral matter, the cross-polar spectrum of matter and transparency of the intergalactic medium. So what I'm plotting here then is the relative strength of that green part with respect to the key matter power spectrum on the first term. So as you can see, naturally at higher redshift we have the highest effect. Nonetheless, the hierarchical structure does make sense, since as we evolve in time, then we are allowing more time to relax the additional energy injection. As a result, recover the temperature density relation. Now, hence, we will have basically a broadband systematic signal for the Lyman-alpha forest power spectrum. But then the question is, how about transforming this to an emerging window of the epoch of reionization? So then what I do here is showing you how, if I change the ionization efficiency, let's say for example how easy it is for ultraviolet photons to escape into the intergalactic medium, then you see that the different shapes of the green power spectrum, cross power spectrum that I showed you before. So what is going on here is, as we go up, there are more ultraviolet photons in the intergalactic medium. As a result, the midpoint of reionization increases, and therefore these are the early reionization model in blue and later reionization model as you go down. On the other hand, if I were to change how easy it is to form the star-forming galaxies, the parent galaxies of these ultraviolet photons that reionize the universe, then we have a similar situation where if we go up, we have more star-forming galaxies, and therefore the midpoint of reionization also increases. Now, you then will argue that well, naturally the shape and width of this smiley face feature does depend on the reionization model. Nonetheless, you can already see that there might be complicated degeneracies looming here, right? Regardless of the degeneracies, the question then will be how easy it is to extract, how efficient can we extract the astrophysics of reionization while simultaneously extracting the cosmological information, the Lyman-alpha forest, and dealing with the nuisance parameters of the astrophysics of the Lyman-alpha forest. So here I show you a preliminary forecast for DESI using the three-dimensional Lyman-alpha forest spectrum. In blue we have the cosmology, so N1 and A1, which are related to the tilt and amplitude of the linear matter power spectrum. Then in red we have the observed flux, which is Lyman-alpha astrophysics, and in green we have the ionization efficiency and the threshold mass for efficient star formation. As you can see, they are indeed quite degenerate for the epoch of reionization astrophysics, but it does seem quite promising. Notice that I did not limit the lower limit manually of the threshold mass, because I'm just showing you what the three-dimensional Lyman-alpha forest power spectrum can do by itself. But in principle, you definitely should take into account a physical limit that is consistent with atomic cooling of star-forming galaxies. So here, what I do is plot the global reionization history, the inferred global reionization history from the 1 sigma errors in our ionization models, in our ionization efficiency models, and threshold mass models. As a result, you can see in the context of the observational constraints and measurements how well can we constrain this. Now, this is interesting because this is a previously unforeseen capability of DESI. DESI is not designed to do this, and without the memory of reionization, it wouldn't be able to. So, the prospects for rich cross-correlation between DESI, which suffer from very different systematics, and other probes of the epoch of reionization astrophysics are going to be quite interesting in the future. So, my summary then is that the key takeaway I want people to have is that gas from mini-voids, plus the fact that reionization is patchy, leave thermal relics in the Lyman-alpha forest that can be used to constrain the astrophysics of the epoch of reionization. There are, of course, theoretical concerns and observational concerns to move this forward, and as a result, there is a lot of work to do, but nonetheless, it's going to be an exciting time. Please reach out if you have any questions.